electronics using these sort of PCVD and micro PCVD machines?
Yeah, so with PCVD capacitively coupled, I suppose is what you have. You have to change the precursors and yeah, and accordingly you have to tune your process chamber conditions
Till
to
now,
be
he sent the
and your
link to
line,
set the
basically
plate
the
and
gas lines
so I just
to meet the organic material requirements.
Okay, so for this reason, can we talk to it with you through mail?
Yeah, sure.
not this one.
Okay, sir. And another thing, as I'm working in a technology college, there are BTech students. Can industrial training or this kind of sort of training can be done in your organization?
Yeah, as I said, we have an internship program which is very rigorous for 6 weeks, and also the selection procedures are also quite rigorous. We normally open it in the month of December, January. So you should be hearing our next internship program very soon. And we have first 2 weeks which goes on with rigorous theoretical sessions, and then we have 4 weeks of project dedicated problem solving projects, and these are not something which are arbitrary, but they form as part of our product portfolio value chain, and each of those end results of those products get integrated into our organization processes, which actually end gets into the products that we are actually we are developing. So these are highly target oriented projects, and these will form multiple training sessions. So they will have technical training, hands-on training, plus they will have to do a lot of documentation, presentation skills, and they also have to do a cost analysis. So many of these things they get to do while they are here during the 6 weeks, which is very rigorous.
Okay, I think he answered. And one more question.
Thank you, sir.
Actually, which organic solvent are you used to make a good thin film coating for organic semiconductor materials? Which solvent is preferred?
Pardon, can you please repeat? Somehow I'm not able to hear. There's a lot of
Okay, I'm
echo.
sorry. Which organic solvent is used to make a good thin film coating for
Yeah.
organic semiconductor materials?
Okay, I mean, if I have to say organic solvent, for example, we have used cyclohexane, we have used heptene, we have used ALQ3 that we used was with a powder, and C60 was also with a powder. So so generally these are the solvents. I mean, when IPA is used for one of the precursor tanks, when we actually process for one of the PCVD chambers. So for a certain organic material processing. So these are the various solvents that we have used. Yeah. Again, these are highly material specific. I mean, we have not focused into the device fabrication part. This is something which our customers do, but we qualify the material processing as a solution.
Okay, nice, sir. I think one more question. I think S. Venkateswaran Jayakumar is having some question. Sir, please, you may ask.
Thank you, Dr. John Prakash, sir. Sir, it's a very excellent presentation. It's a more information about the CVD and PVD. So I am from a chemistry background, particularly organic chemistry background, and we are working in a lab, myself and my student, PhD student. So we are trying to make a thin film, sir, by solution casting technique. And some of the our aim is to coat the biological bioactive chemical in the solid matrix polymer, PEO polymer, polyethylene oxide, and starch polymer. Some molecules cannot able to coat on the polymer matrix. So is it possible both myself and my student come over there, and is it any possible to coat the thin film, to make the thin film in your
Yeah.
method, sir?
Yeah, I think there is a possibility, but we would like to understand the problem a bit more in detail and
Sure, sir.
we can explore this possibly offline. You can write me an email with your research problem and what is it that you are intending at targeting, what are the materials that you are looking at, and then depending on that we will delegate probably a specific process technology which could be employed for your requirement.
Thank you, sir. Very kind of you, sir.
Yeah. Thank you, Dr. Venkatesh. I think there is no more questions. I'm very happy to have you, sir, because you have mentioned what are the material processing techniques and how we developed indigenous equipment to do all this process. Thank you very much, sir. Thank you, Pramod, sir.
Thank you, John, and thank you for the audience for patiently listening me out, and thank you for the organizers in Central University of Tamil Nadu.
Yeah, we'll be in
Thank you
touch,
and
sir.
have a nice evening. Yeah,
Yeah.
bye for now.
Great, sir. Ardra, you may. We'll start the next session shortly. For audience, one information actually that entire event is live streaming, so you may access that one through our YouTube channel also. Ardra.
With this, we have come to the end of our first session. The next session is handled by Dr. Horny Pierre, whose invaluable contributions and unwavering support have significantly impacted the growth and development of Central University of Tamil Nadu. He has done his graduation and PhD from Paul Sabatier University, France. He has completed his postdoctoral research from Northwestern University, USA, and University of Bordeaux, France. He has worked as a CNRS researcher in University of Paris, Diderot, France, and currently he has been working as CNRS researcher in University of Strasbourg, France. His research interests includes supramolecular chemistry and mechanically interlocked molecules, complex system chemistry, supramolecular electrochemistry, and self-assembled monolayers and photosynthesis. Now, over to you, sir.
Okay. Can you hear me well?
Yeah, very well. Welcome, please. Yeah.
Okay, so I'm going to share my screen.
Yeah, please share.
Do you see it? Do you see my screen?
Yeah, it's loading. Yeah, go to full screen.
So that should be now full screen. Okay, good. So if I may start, first of all, it's a great pleasure to be with you. Thank you for having me on board, and I'd like to thank Professor Nagarajan that I knew and met about 17 years ago in Toulouse. And also I would like to thank Professor Prakash, John Prakash, and of course the Department of Chemistry of the Central University of Tamil Nadu. So today I'm going to talk about the research I've been developing so far since I joined the University of Strasbourg, which is based on bacterium core chemistry.
Dr. Henry, please.
Come on. What did you say?
You need to share your entire screen because we are not able to see the whole.
Just full screen. Go to full screen.
That was the first screen. Okay.
You may be viewing it, but we are not viewing. You have to share the entire screen, please.
Okay. Sorry, my mistake. So is it okay now?
Fine.
Do you see the full screen?
Fine.
Okay.
Thank you.
Perfect. No, my mistake. Okay. So actually the picture you see on the screen, it's taken from the lab. Okay. So we have a view over Strasbourg Cathedral, which is one of the most famous monuments here in Strasbourg, of course, and in France. The building you see in front of you here is called ISIS, so nothing related to terrorism. Actually, this institute has the name of the goddess of the Egyptian goddess, and if just you want to know Professor Jean-Pierre Sauvage, who was a Nobel laureate in 1916, has his office right there. So we always feel under pressure when the lights of our lab are switching off before the labs of his office. So my name is Henri-Pierre Jacot de Rouville. It's a very long French name. No one calls me like this because no one can remember it. So feel free to call me HP. That will be definitively fine. So as I was mentioning, I work on this building block, which is called an aquarium core. And I introduced this building block in supramolecular receptors, and more especially, I introduced also these receptors in mechanically interact molecules. Then from supramolecular chemistry to complex system chemistry, there is only a small gap, as long as you introduce some switching properties. I also have some interest, as it was mentioned, about supramolecular electrochemistry and self-assembled monolayers, and also in photoconversions. But today I'm just going to focus on the three topics you see highlighted there. So at the beginning of this research, I was interested in forming molecular tweezers, which can be considered as open microcycle in some ways. They are composed of two recognition units linked together by a spacer, and these two recognition units can interact with a gas to form a host-gas complex. Usually, when we want to distinguish molecular tweezers, usually we can distinguish them according to the nature of the spacer, which could be rigid, semi-rigid, also switchable. Or we can distinguish molecular tweezers according to the host-gas interactions which are involved. And today we are going to talk about pi donor, pi acceptor interactions. And obviously, that's part of my culture since I joined the group of Fraser Stoddart when I was a postdoc. And also, you can distinguish molecular tweezers according to the shape of the recognition units. So the term molecular tweezer was coined by Whitlock in the late 70s with this biscaffeine receptor, which is able to interact with aromatic molecules in water and with a relatively low binding constant. So of course, over the years, you can imagine that the field has evolved and there are many different designs. But what I would like to emphasize with this slide is that when we speak about the switching properties of molecular tweezers, usually the switching unit is incorporated in the spacer. So that could be a photoresponsive unit, a chemical responsive unit, or a redox responsive unit. And in this example, and so far in the literature, there were no molecular tweezers having switchable recognition units. And when I saw this from the literature, I said to myself, why not having switchable recognition units? And I thought that the aquarium core would be perfect to do so. So aquariums are pi extended and also electrodeficient moieties, and they are perfect to interact with pi donor molecules. In addition, aquariums can be seen as pi extended peridiniums, and as peridiniums, they can be reduced, but at a more accessible potential of minus 0.6 volts versus minus 1.3 volt versus SC for just the peridium core. So we have a huge gain in terms of reduction. Also, when the aquarium core is functionalized at the 9 position with a phenyl, we can end up with a new resonance form showing a tritelium motif. So triteliums are part of this family of pH indicators, such as phenolphthalein, that can undergo the addition of a nucleophile. So in our case, the aquarium core is going to interact with a nucleophile, form a new chemical species that we call an acridane, ane for alkane actually. And the previously added nucleophile can be photoejected to restore the aquarium core. So what we see is that with one very small unit, we have some potentially recognition properties and also multi-responsive behavior. And this behavior can be rationalized just looking at the LUMO of the aquarium core, since the major atomic weight is localized at the 9 position. So this means this is the most reactive position. Also, aquariums are chemically robust and functionalizable, and you can functionalize them very easily at the 9 and at the nitrogen positions. So we can derivatize and make some chemistry out of this. So when you look at the literature, aquariums in supramolecular chemistry, it's not something new, but it's not something which is widespread. So as usual in the field, you always find some papers coming from the Lang group who was Jean-Marie Laine was a Nobel laureate in 1987. So basically, I was cooked about 30 years ago about having a bis acrylium receptor. So he made one of them able to interact with aromatic molecules in water, and the other one able to interact with aromatic molecules in organic solvents. Also, acryliums can be used as gas for pi-donor pi-acceptor interactions, more especially with porphyrins. And here you have two examples. But in these four examples from the literature, the switching properties of the acrylium core were not exploited. And when I think of a supermolecular system having acryliums for their switching properties, usually I think of this family of taurotaxanes. So taurotaxanes are composed of two units, a macrocycle and a thread. And at the end of the strand, you have bulky functional groups to prevent the dethreading of the macrocycle out of the thread. So in this case, what we see, or what we understand, is that the acrylium core acts as a stopper and not as a proper recognition unit. So it prevents the dethreading of the macrocycle. Then more recently, the group of Michito Yoshizawa has made this cyclophane, which is soluble as a chloride salt in water and can interact with steroidic gas. So one more time, we understand that the interaction which is involved is not related to pi-donor pi-acceptor interactions. It's more like a sobophobic interaction. And also, when you add some hydroxide ions, a nucleophile, you convert the tetrakis acrylium derivative into the tetrakis acridane derivative. And it's not soluble anymore in water. It precipitates from the solution. So when I saw this, I wanted to come up with a very simple design, which is a bis acrylium tweezer having a terphenyl spacer. The synthesis is very straightforward. What you have to do is to do some pallado-catalyzed coupling conditions to form the dibromo spacer, and then you introduce the acrylium core in the last step. The NMR of this molecule at room temperature is very simple. So this suggests that we have some free rotations in the spacer and also in between the spacer and the acrylium cores. And this was also confirmed if you cool down the temperature of the sample and you see a broadening of the NMR, meaning that you start freezing the rotations. The FT calculations allowed to find 4 different minima for the molecule, what we call the U-shape conformation. So the U is formed by the molecule itself. The T-shape formed by the two acryliums, it's formed a T. H-shape or W-shaped conformation. So basically we have 4 minima. Okay, no big deal, because we can have still some interactions with a guest. So we tried many different guests, many good donors. One of them was TTF, and we always ended up to the same conclusion. So first of all, when you want to look at supramolecular interactions, what you do, you run a proton NMR titration, and you see that over time we have a shift of some of the signals. Then also you can sometimes follow it by UV visible spectroscopy. So in this case, we have the increase of what we call a charge transfer band at, let's say, 750 nanometers, which corresponds to the partial electron transfer from the TTF to the acrylium cores. And when I fitted this data to a mathematical model, actually a one-to-one binding model, I ended up with a very low binding constant of 10 molar minus 1. So basically it's ridiculous. It's like if we have no interactions. So fortunately, we were able to grow crystals, and the molecule crystallizes in its U-shaped conformation with one pF6 in between the two acryliums. So the acrylium distance is roughly 8 angstrom, which is too big actually to ensure pi-pi stacking interactions. And we try to understand how we could optimize the design of the molecule. And if you look carefully at the spacer, it's distorted because there is a steric clash. You have 3 CH bonds pointing in the bay area of the spacer. So this steric clash moves apart the two acryliums, and like this, you reach a distance of 8 angstroms. So this means that if you want to have the two acryliums close to the optimum distance for pi-pi stacking interactions, namely 7 angstrom, what you have to do is to get rid of the steric indifference in the Bay region. So what we've done is that we changed this central CH by a nitrogen. And here we have the new design of the second generation of the molecular tweezers we designed. So the synthesis of this molecule is slightly different from what it was before. Actually, what we had to do was to form the acrylium core, but it has a positive charge and sometimes it leads to some tedious purifications. So what we've done is that we wanted to get rid of this positive charge. One way was to reduce the molecule into the corresponding hydroacridine. Actually, this molecule is slightly unstable under air since it slowly reoxidizes into the acridinium derivative, but still we can work with this, form the semi-rigid spacer, and finally, in the last step, we can oxidize using DDQ and get the molecule. And the first evidence or proof of the existence of this molecule was provided by mass spectrometry. And when you think about it, it's very unusual because as an organic chemist, what you do is that you run an NMR first. And why this? We were not able to see it. Actually, that was the first NMR I got here in the middle. At room temperature, you see it's extremely broad. So from the previous study, we thought that we had different conformations. And if you are in exchange, you end up with a broad signal. So to confirm this, what we've done is that we heated up the solution, and indeed we have a simplification of the spectrum. And at low temperature, so we have to change solvent from acetonitrile to acetone. At low temperature, we have a new proton NMR. And obviously, we have a very symmetrical molecule. So we have we have only one set of signals for each protons. So this means that eventually we have one conformer in solution. So then to confirm the structure of the molecule, actually we were lucky because we were also able to grow crystals. And this molecule crystallized in the form of a 9-twine dimer. So if you look at one of these tweezers, actually the distance between the two acryliums is roughly 7 angstrom, which is perfect to ensure pi-pi stacking interactions. And then the spacer is totally flat and can act as a gas for another tweezer. So that's how you assemble, at least in the solid state. So the question that came is that do we have this dimer in solution or not? So to answer this, what we've done is that we ran some dilution studies. So for the most concentrated solution, we do have a broad signal, meaning that we are in an exchange regime. And upon dilution, we have a simplification of the NMR, meaning that we dissociate the assembly and then we form a monomer. Then when we took these 4 solutions at low temperature, what we saw is that we have a new chemical species for the most concentrated solution, which is actually the dimer. And when we dilute at low temperature, this time we see that there is the presence of the dimer and also the presence of the monomer at the same time. So basically we can freeze the monomer dimer equilibrium, and like this we can estimate a binding constant at low temperature. And we can do it also at different temperatures, and like this we can estimate the thermodynamic parameters of the system. So this monomer dimer equilibrium was also confirmed by at high temperature, because at the 4 previously studied concentrations, when you heat up the solution, you end up with almost the same spectrum. So this is expected since we work with weak interactions, and heating up will dissociate the assembly. So in our case, we have the monomer at high temperature. Also, this equilibrium was confirmed by a solvent polarity study. So when we have a 100% of acetonitrile, we have a broad spectrum. And upon addition of the MSO and going into pure DMSO, we end up with the spectrum of the monomer, which is expected because DMSO is a competitive solvent. So one proof that we have this dimer in an organic medium was provided by mass spectrometry. And when you look at the first mass spectrum we got with a fairly concentrated concentration solution, we have different peaks corresponding to the dimer, trimer, tetramer, and pentamer. So now the idea is to say that if the dimer is a specific aggregate, we should basically keep this signal if we dilute the injected solution into the mass spectrometer. And actually, this is what we observed. We have one peak which survives, which is the peak of the dimer. Also, what we understand from these studies is that the dimer is not a, how can I say, a stabilized species in organic solvents, so we have the tendency to dissociate. So you have to boost the association, and one way is to change solvent. So we converted the PF6 salt into the corresponding chloride salt, then the molecule becomes soluble in water, and what we wanted to do is to use solvophobicity. So indeed, the molecule is soluble in the solvent at different concentrations, actually the same 4 concentrations as previously studied. And we do see only one chemical species, which is the dimer. So thanks to this experiment, we can estimate a binding constant, which is 10 to the 5 molar minus 1, which is a huge gain in comparison to what it was in acetonitrile. So one proof that we have this dimer in solution was provided by the NOSI spectrum. So we can see some through-space correlations between what I call the gamma proton and the methyl, beta proton and the methyl. So gamma and beta protons of the periodic core and the methyl of the acrylium core. So if you have a NOSI correlation, this means that they are close in space, and this is what we expect from the solid state structure. Another proof of the dimer formation was provided by DOSI experiments. So actually, under conditions where you have the monomer and the dimer, so in acetonitrile, under dilute conditions and at low temperature, you do have 2 diffusing species, one which is faster than the other one, which is the monomer. And thanks to the diffusion coefficient, we can estimate an hydrodynamic radius of roughly 7 angstrom for the monomer and also 7 angstrom for the dimer. This value of 7 angstrom for the dimer was also confirmed by those experiments in D2O. And this value of 7 angstrom is also in good agreement with what we can observe for the solid state structure. So I hope I was able to convince you that we have this dimer in solution in different solvents. So of course I wanted to play with this family of molecules, and we looked at the influence of protonation. So we changed the N-methyl acridinium by the NH acridinium, so protonated acridine. So it has roughly the same behavior in acetonitrile as the methylated compound. So at different temperatures, we can estimate a binding constant because we have a different ratio between the monomer and the dimer. And like this, we can go for a van 't Hoff plot analysis that allows you the determination of the entalpic and entropic contribution of the molecule in this solvent. What you can do in one solvent, you can do it in other solvents. So we tried a bunch of them. What this graph tells you is that if you go on the left part, you will favor the association. And this goes with increasing the polarity of the solvent. And this is verified for almost all solvents except methanol. So this was a bit surprising to us, more especially when you know a little bit your literature. And we looked at this paper called A General Model for Solvation Effects on Apolar Binding, which was written by François Didrich. And what it showed is that for pi-pi stacking interactions between aromatic moieties, though, we have an increase of the binding constant or decrease of the delta G value as you increase the polarity of the solvent. So what happens in our system? That was the question. So to understand, we compared the NH tweezer by the N-methyl tweezer. And actually what we do see is that for the N-methyl, we have an inversion of this tendency. Also, we have exactly the same thermodynamic parameters for both systems in acetonitrile and a huge change in methanol. So what we hypothesized is that methanol allows proton deuterium exchange for the N proton acridine and protonated acridine, and basically your acrylium core is less electrodeficient, and like this you dissociate the dimer. We also wanted to trigger the dimer formation by different switches. So one of them was done by protonation, actually very simple, but we did a biphasic experiment, an NMR experiment. So in the same NMR tube, you have two phases. The bottom layer was DCM and the top layer was water. And you can probe these two phases, or what you have in these two phases. So initially, for the bisaccharidine derivative, we have only the molecule in DCM and nothing into water. And then when you increase the amount of sulfuric acid, in the tube, what you see is that you have a decrease of the precursor in dichloromethane and an increase of the dimer in D2. So that was a nice experiment, but it was a bit useless because we cannot assess what's going on in between the two states. So in other words, you have no monomer even protonated into water and no dimer into DCM. So it's like if everything happens or occurs at the interface. So we've done some molecular dynamics simulations. So you cannot create a bond. So Alain Chaumont, who did these experiments or these calculations, started from three case scenario. The first one was the initial state with the non-protonated tweezer in DCM and then some sulfuric acid in water. And you see that mainly the tweezer remains in DCM. Then when you start from the protonated molecule, it stays mainly at the interface. And finally, when you start from the dimer, this dimer also mainly remains at the interface, but still you have some in water. So basically, these calculations confirm that everything occurs at the interface. So let me summarize what we've seen so far a little bit. So we have two systems. Both of them crystallize in the form of entwined dimers, and they have the same thermodynamic parameters in acetonitrile. Then what we wanted to check is that do we have some pi donor, pi acceptor interactions in between the spacer and the acrylium cores? So to answer this, what we've done is that we enriched the spacers with methoxy groups, and we have two new systems, the N-methyl and NH dimers. So these two molecules, they also crystallize as in their dimeric form. And now when you compare the thermodynamic parameters, you have an increase of the enthalpy contribution, meaning that you stabilize the system by weak interactions. So this goes for some pi donor, pi acceptor interactions. This was also confirmed by electrochemistry. So what we know is that at, let's say, roughly high temperature, 30 Celsius, we have only the monomer. So if you look at the electrochemistry, we have one reduction peak, which is the peak of the monomer. The other peak is just a reference, which is commonly used in electrochemistry, which is ferrocene. Then also what we know is that when you cool down the temperature, you will form the dimer, and you see that you have a shift of the reduction potential towards the more negative values. So this new potential that you can assess is the potential of the dimer. If you complete the square scheme analysis, you can estimate a binding constant between the reduced chemical species, and the new binding constant is 3 times lower than it is for the native form. So in other words, when you add electrons to the acrylium cores, you will enrich them, and then you are going to dissociate the assembly. What was done for the non-methoxylated tweezer can be done for the methoxylated tweezer. So in this case, what we know also from the thermodynamic parameters is that we have a favored binding constant for the methoxylated derivative in comparison to the non-methoxylated derivative. But what was very surprising to us is that when we look at the binding constant of the reduced species, we have a huge decrease for the methoxylated compound in comparison to the non-methoxylated compound. And this goes well with our first or initial interpretation, which was if you enrich either the aquarium core or the spacer, you will go for the dissociation of the reduced chemical species. So that's definitively in favor of pi-donor-pi-acceptor interaction. Then also what we wanted to look at was the influence of the position of the nitrogen atom on the semi-rich spacer. So instead of having only one periodic core, this time we have two of them. The synthesis is straightforward again, so we can form the dibromose semi-rich spacer under parallel-catalyzed coupling conditions, and then we introduce the aquarium cores in the last step. Unfortunately, we were not able to grow crystals for this molecule, but one way to make sure that it has exactly the same behavior as the initial compound is that you can compare them into either water or DMSO. So in water, you have exactly the same chemical sheets for the aquarium protons, meaning that they are in the same environment, in the environment of a dimer for both systems. And in DMSO, you do have also the same chemical sheets for the aquarium protons, meaning that they are also in the same chemical environment. Basically, you dissociate the dimers and then you form the corresponding monomers. Also, what was super interesting to look at was the dilution study for this new system. And when you dilute, you have a broadening of the signals, meaning that you start being in an exchange regime. So you start dissociating the dimer into the corresponding monomer. So in other words, if you want, the binding constant of this new system is lower than it is for the previous system. Then we looked at a one-to-one mixture of tweezer A having only one pyridine core and tweezer B having two of them. And you have the corresponding proton NMR spectrum in D2O. What you see is that you have only two chemical species in D2O, which corresponds to the homodimers. So when you mix tweezer A and tweezer B, you end up with dimer AA and dimer BB with no formation of ABs. This is what we call narcissistic subsorting process. Then this solution, the one-to-one mixture, is stable over 3 weeks on the benchtop. And also you can heat it up, nothing happens. So it's like if we have reached thermodynamic equilibrium. To make sure of this, what we've done is that we took this sample, that's the same sample, then we evaporated D2O, and we put everyone into DMSO. So what we expect is to dissociate the dimers into the corresponding monomers. Why do we want to do this? It's like when you play poker, actually you want to shuffle cards in order to have a new game. That's exactly the same idea behind this. Then what we've done is that we evaporated DMSO again, and we added D2O. And you see that you have exactly the same spectrum as before. So this means that indeed we are under a thermodynamic control. And this was very surprising to us because we have tweezers of the same size, the same shape, and involving the same kind of interactions. But what we know is that this new dimer formation has a binding constant which is lower than the previous one. And if you do the math, only one order of magnitude is enough to drive for the formation of the homodimer AA, and then only B molecules can interact with B molecules to form the homodimer BB. Also, the FT calculations told us that we have a most favored interaction between the nitrogen and this CH bond, kind of like an electrostatic interaction, which is more stabilizing than it is for the other tweezer. Also, what we see is that we are very far from the initial goal, which was to do some host gas chemistry, mixing two compounds to form a host gas complex. What we do is that we have self-complementary behavior. So if you want to prevent the dimer formation, what you have to do is to form the corresponding microcycle. And this microcycle actually was done by my former PhD student, Johnny Yu. He was very talented. So Johnny made the microcycle under Grubbs conditions. That was the last step to form this double bond. The yield was 98% because the microcycle precipitates from DCM, which was the solvent used. and then he just had to filter the solution to get the pure compound. Also, Johnny was very talented and lucky because he was able to grow crystals. And we see that the molecule indeed crystallizes with one benzene molecule inside its cavity. So this benzene comes from the crystallization conditions since benzene was used as a non-solvent. So we can start thinking here that this receptor is good to do some host gas chemistry, more especially in solution. So one example I show you is with perilene. So for the one-to-one mixture of host and guest, you have upfield shifts of most of the protons in comparison to the isolated components. So this means that you have some pi-pi stacking interactions, except for the O prime proton, which is downfield shifted. And O prime is inside the cavity of the microcycle, meaning that the gas goes inside the cavity of the receptor. Also, during this experiment, we observed a color change. So the microcycle is yellow, perilene is slightly yellow in solution as well. And when you do the one-to-one mixture, you have a greenish color. This greenish color is the result of the appearance of a charge transfer band at 600 nanometers. So one more time, we have a partial electron transfer from the donor, here perilene, to the aquarium cores. Thanks to UV visible titration, so following this charge transfer band, we were able to estimate a binding constant of 1200 molar minus 1 in DCM, which is a huge gain in comparison to the previous systems. So we were right to form the microcycle. It does prevent the dimer formation. Then also, Johnny looked at the chemochromic properties of the microcycle. So he converted the bis acridinium derivative into the corresponding bis acridane upon addition of hydroxide ions. You can follow the dearomatization of the aquarium cores by proton NMR spectroscopy, and this system can be fully aromatized under acidic conditions and more especially using TFA. Then this new microcycle has no affinity for perilene. Why? Because first of all, you have a dearomatization of the aquarium cores, a loss of their negative charge. So basically this motif is more like a diarylamine, which is an electron-rich building block and does not want to interact with perilene. And also, the last thing is that you have a distortion of the cavity of the microcycle since you have a hybridization change from the C9 atom here, from a carbon sp2 to a carbon sp3. Fortunately, the recognition properties can be fully restored upon addition of trifluoroacetic acid, and this is 100% reversible upon addition of hydroxide ions. So if you want, we have an on-off system for the recognition of perilene. So long time ago, about 5 years ago, I was showing these results to Jean-Marc Vincent, who is a senior CNRS researcher working at the University of Bordeaux. And Jean-Marc is an expert in perfluorocarbons. So alkanes which are fully fluorinated. And so I knew a little bit about these solvents, but Jean-Marc told me a lot. First of all, he told me that they are chemically inert solvents. So for instance, this mouse can survive into a perfluorocarbon, actually breathe the solvent, breathe the oxygen which is inside the solvent, and obviously it survived like this for 3 hours, but for sure the mouse was traumatized forever, and I don't know, I cannot tell you how long it did survive after this experiment. Then also, perfluorocarbons are non-miscible with water and organic solvents. So you will have 2 phases, and perfluorocarbons, they have a very high density of 1.8. So this means they will be often the bottom layer. And Jean-Marc told me the following thing. Since these solvents do not like to interact with any other molecules, they should be perfect to do some host gas chemistry. They cannot be in competition for the assembly. And also, since they do not like to interact with any other molecules, they should have some sorophobicity, a little bit like water, but in their ways. So to help you understanding this, I'd like to introduce to you this polarity scale, which is called ENT scale. N means normalized. So it goes basically from 0 to 1. From 0 to 0.3, you have the apolar aprotic solvents. up to 0.5 the polar aprotic solvents, and then up to 1 the polar protic solvents, with 1 being water. What about perfluorocarbons on this scale? They have a polarity of minus 0.05, which makes them the least polar solvent known so far in the literature. So they are even less polar than their corresponding alkanes. What is fun with this solvent is that they have also a variety of structures, so you can play with some of their physico-chemical properties, such as the boiling point, and you can see that we can go from, for instance, from 50 Celsius to 150. So we can do basically what we want with them. And also, what you have to know is that their boiling point is often lower than it is compared to their corresponding alkenes. So when Jean-Marc was telling this to me, I was thinking a lot about how can I bring my receptors into a perfluorocarbon phase. So one obvious strategy is to attach a long fluorophilic chain on the receptor. But this might lead to some very tedious synthesis or even purifications, and was not super happy about this. So I was already like, yeah, Jean-Marc, I'm not sure it's going to work nicely, because having a long fluorophilic chain with dicationic molecules, I don't think it's going to work. But Jean-Marc told me, no, HP, you have all it wrong. I can bring a dicationic molecule, lithium twice by P, from DCM, so it's orange, okay, from DCM to PFC phase by addition of this highly fluorophilic carboxylic acid. And actually, how does it work? This carboxylic acid is going to form a carboxylic acid carboxylate counterion, which is itself supramolecular, stabilized by a H bond in between the two units. And this counterion will be fluorophilic enough to bring dicationic molecule from an organic phase to a PFC phase. So what we did is that we used our bisacridane macrocycle in the presence of the same highly fluorophilic carboxylic acid. And actually, it did two things. The first one was the rearomatization of the acrylon cores, the formation of the highly fluorophilic counterion that brought the molecule from DCM to the PFC phase. Then also, we have no leaching of the macrocycle into DCM. So if you want to have it back into an organic phase, what you have to do is just to add few drops of methanol that is going to act as an H-bond competitor for the counterion. So you will have a counterion which will be less fluorophilic, only the carboxylate counterion, and this time the molecule goes back into the organic phase. Then also we wanted to exploit our enriched fluorophilic phase with fluorous phase with the macrocycle for the extraction of perylene from DCM. So this is what we did. After stirring, we have a color change from yellow to green. So this means that you have the formation of a host gas complex. And then upon changing DCM by fresh DCM, you can release the captured gas. And this experiment, thanks to few control experiments, allowed us to estimate a binding constant for the in the PFC phase, which is 2 orders of magnitude higher than it is in DCM. So basically, Jean-Marc was right. Perfluorocarbons can boost the association between a host and a gas due to their solvophobicity. And then we went a little bit further. We looked at a 1-to-1-to-1 mixture of perylene, anthracene, and naphthalene. So they were in the DCM source phase, and you have the GC chromatogram of this DCM source phase, and you do see 3 peaks. After stirring, we have a color change. So we have a host gas complex which is formed, and upon changing DCM by fresh DCM, we can release the gas into the DCM receiving phase, and you have only 1 peak in the GC chromatogram for this phase, which is the peak of perylene. So in other words, we were able to selectively extract perylene out of a complex mixture of polyaromatics. And if you want to do it by column chromatography, you will always end up with a complex mixture of polyaromatics. So that's pretty efficient in our case. How do we rationalize this? Actually, perylene is the most pi extended system, so that's the better donor because the HOMO is going to increase in energy. So that's the best donor, and then it's going to be more prone to give electrons to the acrylium cores. So you have a thermodynamic control on the extraction. Also, you reuse the PFC phase 3 times with no loss of real activity. So that's very efficient system, and you can use it several times. We also looked at the electrochemistry of the microcycle. It has a first reversible reduction wave, which corresponds to the injection of 2 electrons, 1 per actinium, as supported by spectroelectrochemical data. And then when you add perylene to the solution, what you see is that you have a shift of the reduction potential towards the more negative values. And this makes sense because perylene gives some of its electronic density to the acrylium cores. So basically, they are less prone to accept electrons from the electrode. And that's why you shift the potential towards the more negative values. Thanks to this shift, we can do a square scheme analysis, and we can end up with a binding constant of 50 molar minus 1 between the reduced microcycle and perylene. So one more time, if you add electrons, you will dissociate the assembly. So with this microcycle, we've done also a 2-row taxane. So just for a kind reminder, we have a rotaxane. The 2-row taxane is composed of 2 units, a microcycle and then dumbbell. And then dumbbell has 2 bulky stoppers in order to prevent the dethreading of the microcycle from the thread. So when you want to make a rotaxane, you have several strategies. The first one is what we call the threading and stoppering approach. So first of all, you do the host case complex, and then you introduce the stoppers in the last step, and like this, the microcycle is trapped. Another way is called the clipping strategy. So you start from the thread itself, and then you do the macrocyclization of the compound around the thread. So that's the clipping strategy. You can also have what we call the slipping strategy. So these times, the 2 components are already formed, but there is a trick. The stopper is a good stopper at room temperature, but not very good at high temperature. So if you heat up the solution, you will have the rotaxane, and then you cool it down, you have a stable molecule again. And the last strategy is called the active metal template. So the microcycle acts as a ligand for a metal cation that is going to catalyze the dumbbell formation, and then you end up with the 2 rotaxane. So in our case, what we've done is that we started from dumbbell having a pyrene recognition site, and then we did a clipping strategy, and we got the 2 rotaxane in a decent yield of 18%. Then what was fun with this molecule is that it's soluble in a variety of solvents, having a bunch of different varieties from DCM to methanol. So what you see for this molecule in the different solvents is that you have almost the same chemical shift for most of the protons. So this means that they are in the same environment. And this clearly suggests that we have the microcycle in proximity or vicinity of the pyrene recognition site. And this was also confirmed by variable temperature experiments. So to give you an idea on what's going on, we've done some molecular dynamic simulations. So what you see here is just the host gas complex. And over the time scale of the simulation, we have no real dissociation of this assembly. So we have basically no shuttling, okay? The microcycle resides at the same position. Then we wanted to look at the bis acridane derivative, so we added hydroxide ions. So the proton NMR of this molecule shows that you have peaks from the pyrene recognition sites, which are closer to what they are for the free dumbbell. So this means that the microcycle moves away from pyrene. Then also, you have only 2 sets of signal for this proton, which is called the that we call the MA proton, which is the proton of the stopper. So if you have only 2 sets of signals, this comes from the microcycle, which could be trans and cis isomer of its olefinic bond. So this was also only 2 sets of signals at low temperature. So we have no real dissymmetry of the 2 stoppers due to the motion of the microcycle. So we have a free shuttling of the microcycle along the dumbbell since there is no real specific interactions. So one more time to give you an idea on what's going on. Here are some molecular dynamic simulations. So in red, you have the microcycle, in yellow, the dumbbell, and over the time scale of the simulation, the microcycle moves from one side to the other side of the dumbbell 5 times. So I hope it's going to do it because I saw it at the beginning of the video. Maybe I can just wait a few additional seconds. Yeah, here we go. So we see that the microcycle moved from the left side to the right side. So no real specific interactions, and the dethreading is prevented by the stoppers. Then we looked at the electrochemistry of the rotaxane. But before explaining the electrochemistry of the rotaxane, let me go back to the electrochemistry of the macrocycle. So I was mentioning that we have a first reversible reduction wave, but this reversibility is affected by a second reduction process, which is itself irreversible. So in electrochemistry, that's called an EEC mechanism. So you inject the first set of electrons, then the second set of electrons, and then the molecule transforms itself, becomes something else, and has another redox potential. So what about the rotaxane? It has exactly the same behavior, an EEC mechanism, but both reduction waves are shifted towards the more negative values. So this is expected for the first redox process because the recognition site gives some fixed electronic density to the acrylamide cores. But even after reduction, the microcycle still feels the presence of pyrene since it's harder to reduce. So you have no real shuttling even after reduction. Then we wanted to look at the in situ conversion for the bisaccharidian derivative. So to do this, we have to change solvent from DMF to dichloroethane. So in dichloroethane, the first reduction process, which corresponds to the injection of 2 electrons, is splitted. So that's the same process. And upon addition of hydroxyl ions, what you have, you lose the reduction or the electrochemical signal. And upon addition of TFA, you restore the signal. So if you want, we can monitor the mechanical state of the rotaxane by electrochemistry, because when there is no shuttling, we have a redox signal, and when there is shuttling, there is no redox signal anymore. Then also, what we understand from this cyclic voltammetry is that we can differentiate the injection of the first electron and the second electron. So we can reach the mono-reduced species, and this was prepared by the addition of a little bit less than 1 equivalent of cobalt to zinc. And then we looked at the EPR spectrum of the molecule. So that's the red trace for the rotaxane, and to understand this, we had to compare it to the microcycle and to a model compound. So for the model compound, you have a hyperfine cupping, which is monitored, so this is what you expect. In the case of the microcycle, you have a broadening of the signal. So this means that you start having a spin exchange regime. So the electron moves from one redox center to the other one. This makes sense because they are in close proximity. And in the case of the rotaxane, we are in an intermediate situation. So this means that you slow down the spin exchange. And this was very curious to me, because I thought that if I have some additional orbitals in between the 2 redox centers, I should favor the spin exchange and not disfavor it. So DFT calculations told us the following thing, is that if you look at the microcycle, the mono-reduced microcycle, you have a collapse of the structure, and the 2 redox centers are in close proximity of 3.5 angstrom. Of course, this collapse cannot occur in the case of the rotaxane because you have the recognition unit in between. So the 2 redox centers are far away, and like this, you slow down the spin exchange. So this is what I wanted to share with you on the rotaxane. And now we are going to speak a little bit of photochemistry. So I was somehow hiding something to you since the beginning, because I just recently understood what happened to this very specific building block, which is an acrylium core functionalized at the 9th position with a 2 pyridyl. So this molecule has a yellow color in solution, and then when you leave it under light, it turns green. So you can follow the photoconversion by UV visible spectroscopy. So instead of having a molecule absorbing below 500 nanometers, now you have something that absorbs from 300 to 800 nanometers. Then, of course, as an organic chemist, what you want to do is to run a proton NMR. But then, in this time, I had no signal. So this suggests that I have a radical. This radical was confirmed by EPR spectroscopy with a G value of 2. So this means it's an organic radical. And then what we've done also is that we use the Evans shift method that allows you to probe the number of unpaired electrons for the molecule. And in this case, we had only one unpaired electron. Then for quite a long time, because the story has started, this observation has started in 2020, the last characterization I had for this molecule was provided by mass spectrometry. And you see that the photo product has the same chemical structure than the precursor, but with one proton which is missing. So this proton missing, maybe you understood what happened, but for those for whom it's a little bit more difficult, here is the answer, the solid-state structure. So what we see is that the photo product is the result of the formation of a new bond, this nitrogen-carbon bond, which is photoactivated and undergoes a cyclodehydrogenation. So this molecule, we named it a viridium because viridis in Latin means green, and also it's a radical cation, so it has a positive charge, so that's why it has the suffix ium, so viridium. This molecule stacks along the A-axis of the crystal with an interplanar distance of 3.3 angstrom, which is below the sum of van der Waals radii of two carbon atoms. So they are closer to what they should be. So this means that you have an additional interaction, and I'm going to explain this in the next few slides. But first of all, I'd like to go for the stability of the radical, because indeed the crystals were grown under ambient conditions. So you can follow the stability of the radical over a 2 months period. And actually, this represents the variation of the different maxima of the viridium radical cation. And you see that after 2 months under ambient conditions, so air, light, and moisture, you have only a 10% loss. So that's a very robust radical, no real reactivity. And also the structure of the radical was provided by NMR spectroscopy. So of course the radical is NMR silent, but then when you add an oxidant, here NOBF4, you go for the oxidized species, which is diamagnetic, and then you can record an NMR. So this NMR corresponds to 14 different protons. When you go for the COSY, HSQC, HMBC, C13, and everything you can want, you have, it's in good agreement with this chemical formula. And also when you compare the proton NMR of the oxidized photoproduct to the precursor, you see that you have a non-speed shift of most of the protons, meaning that you have an extension of the pi system of the molecule. Then we looked at the electrochemistry of this molecule, because obviously it can be oxidized very easily. So actually it can be oxidized and also reduced, and you have two reversible reduction processes. Also, we calibrated this cyclic voltammetry using ferrocene, and ferrocene is stable under air, okay? So if you have a potential which is an oxidation potential which is above ferrocene, this means that most likely your molecule will not be sensitive to oxygen, and this is what you observe. Then rotating disc electrodes, disc electrode experiments tells us that we have two monoelectronic processes. And also, this radical cation is a good candidate for electrochromism, because when you oxidize the molecule, you have a color change from green to orangish, and when you reduce, from green to pinkish. How can we rationalize this redox potential in oxidation? So let me introduce the reduction potential of pyridinium cores. So how difficult it is to inject an electron, and all potentials are referenced against ferrocene compound in this case. So we have for just a regular pyridinium a potential of minus 1.7 volts. So if you look at the LUMO of an acrylium, it has the major atomic weight at the 2, 6, 4, and nitrogen positions. So if you want to stabilize the injection of an electron, what you have to do is to extend the pi system at these positions. And indeed, you see that the redox potential is higher, so it's easier to inject electrons. If you want to stabilize even more the electrons, so you have to change the functional groups for something which is more relevant, such as an electro-withdrawing group, which could be an ester functional groups or another pyridinium, which is itself electroactive. So we go for the very famous paraquat derivative. And if you functionalize the paraquat derivative with 4 ester functional groups, you can even go for an oxidation, you can go for a reduction potential of minus 0.3 volts versus ferrocenium ferrocene. What about the acrylium core on this scale? It has a polarity of roughly minus 1 volt because you already extend the pi system of the pyridinium at the right positions. And what about the veridinium, oxidized veridinium? So this time you can see it as a bipyridinium derivative, which is extended, pi extended at the right positions to stabilize the LUMO. So like this, you can reach a potential of 0.3 volts versus ferrocenium ferrocene. We looked also at the photophysics of such a molecule. So if you want to understand the photophysics of a molecule, you have to compare it to model compounds. So we compared it to the 9-phenyl and the 3-pyridyl. What you have to look at is the fluorescence quantum yield and lifetime, which are decreased for our system in comparison to the two model compounds. So this is in good agreement with the fact that the introduction of the 2-pyridyl core will go for dark relaxation processes, and this is in a very good agreement with the fluorescence quantum yield of 33%. So basically 1 photons over 3 trigger the formation of the radical cation. The last thing we've done in order to understand what was going on in the photoconversion was following the radical cation formation by EPR spectroscopy. So under air, and after 15 minutes, we reach a plateau and we get the blue signal. Under argon, of course, this can never happen because you need air to abstract a proton at some point. And even after 15 minutes, you can never reach the formation of the radical cation. But what was interesting is that we worked with a sealed EPR tube. And if you leave this tube under air, you will slowly restore the blue trace from the red trace. So this clearly means that we have an intermediate, and the FT calculations told us that this intermediate is the result of the nucleophilic attack of the nitrogen atom at the 1 position of the acrylium core. The activation barrier for the ground state is too high, so it's not thermally favored. But once you go for the excited state, you see that the activation barrier is decreased, and that's how we form the radical cation. Then also I was mentioning about a special interaction for the radical cation. So if we change the counter ion from PF6 to chloride salt, the molecule becomes soluble in methanol, and it has exactly the same spectrum as it was in acetonitrile. However, if we add a little bit of water, and more water actually, we go for a drastic change in the UV. So we have a blue shift of most of the transitions below 800 nanometers, and also an increase of the charge transfer band in the near IR, which clearly suggests that we have a radical interaction between two of them. So we have a pi dimer. Then this dimer formation was confirmed by the variation of the charge transfer band, which is linear as a function of the square of the initial concentration in monomer. So this means that we have only a dimer and no trimers, no tetramers, and so on. So thanks to this data, we can estimate a binding constant of 2.2 10 to the 6 molar minus 1 in water, which is kind of reasonable. What about perfluorocarbons? So we extracted the dimer from water into a PFC phase, more especially perfluorohexane, using the same strategy as before. So our counter ion, highly fluorophilic counter ion, and we have a good efficiency of 64%. The UV visible near IR spectrum is exactly the same as what we expect for the dimer into the PFC phase. So we do have some phobophobicity. And then if you want to probe the thermodynamics, what you have to do is to add another solvent into the PFC phase. So perfluorocarbons are unmiscible with few of organic solvents, and one of them is trifluorotoluene. So, and indeed, when you add trifluorotoluene, which has about the same polarity as DCM, you have a decrease of the charge transfer band in the near IR and then the restoration of the spectrum of the monomer. So basically you dissociate. So what about the thermodynamics? So in water and perfluorocarbons, we have almost the same delta G value, meaning that we have almost the same binding constant, which is 10 to the 6 molar minus 1 in both solvents. So one more time, we confirm that perfluorocarbons have some phobophobicity. And this time, perfluorocarbons, we can measure it. It has almost the same phobophobicity as water. Then also what we've done is that we compared the thermodynamic parameters in trifluorotoluene and in perfluorocarbon trifluorotoluene in a 9:1 ratio. So what we expect is that when we increase the percentage of perfluorocarbon, we have a decrease of the delta G value, so an increase of the binding constant. We have a dimer which is more stable, which is the result of an increase of the enthalpy contribution. But what was very surprising to me is that when we look at the entropic contribution, we have a decrease of its value, meaning that we are going to have some order in the system. So this order cannot come from the dimer because the dimer is the same in trifluorotoluene and in the mixture of solvents. So we cannot order better the dimer than it is a dimer actually. So then what we have in terms of interaction, we have the interaction between the solvent and the dimer and between solvent molecules. What we know as well is that perfluorocarbons do not like to interact with any other molecule. So we can exclude the interaction between the dimer and perfluorocarbons. So what remains is only the interaction between perfluorinated molecules. So basically what we probe here is that we have some ordering of the solvent of the perfluorocarbon phase. So that was one of the only studies so far for which we can probe the ordering of perfluorocarbon phases. So the last system I'd like to show you on this acrylic core chemistry is related to an allosteric control. So allostery is commonly found in nature, more especially in hemoglobin. So it has 4 interaction sites for oxygen molecules. The binding of the first oxygen molecule is going to increase the binding constant of the 3 others. And this is what we call a positive allosteric control. So in other words, you have a receptor having an allosteric site and an active site. The first oxygen molecule, in our case, which is an effector, is going to interact at the allosteric site, changing the shape of the receptor, and like this, it can accommodate other gas. If you have a positive allosteric control, you can also have a negative allosteric control. So this time, the effector is still going to interact at the allosteric site, changing the shape of the receptor, but this time, you cannot accommodate a gas as efficiently as before. So when you look at artificial allosteric systems, many of them involve porphyrins, and then the allostery can be controlled by the addition of cations or the addition of anions. It can be under redox control or photochemical control. So why these systems, they use porphyrin? Because porphyrins are super nice molecules. They are aromatic. You can functionalize them at the beta and meso positions. They can also interact with small molecules according to metal-ligand interaction or according to pi-pi stacking interactions. Then also they have very interesting physico-chemical properties. So you can irradiate the porphyrin core at their most intense band, which is the solid band at, let's say, 450 nanometers, and then you emit light at 700 nanometers. Also, porphyrins can be oxidized And you can tune the oxidation potential according to the metal cation you put inside the free base. So you can see you can play with their properties very easily. Then since I'm closely working with a porphyrin chemist, Valerie Heitz, we decided to come up with our design for a receptor, which is a bis porphyrin acrylium conjugate, and that's a molecule giving a molecular tweezer. This molecule was made by a shared PhD student, Emei Edo Osagi, and she made this molecule in few synthetic steps that's very straightforward as long as you have the right building block, which is this acrylium benzaldehyde. So this allows the formation of the porphyrin core under lentic conditions, and then what you can do is dimerize this porphyrin acrylium conjugate under Krebs conditions. So this receptor can interact with gas, and more especially with ditopic ligands. So for instance, 4,4' bipyridine. So what you see is that for the receptor, the most affected protons are the protons of the porphyrin. So this makes sense because this is where it's going to interact the ditopic ligand. And then also you can follow this interaction by looking at the solid band. And indeed, you see a shift. And thanks to this shift, you can estimate a binding constant of 1.7 10 to the 5 molar minus 1 in BCM. So that's kind of like a regular binding constant for this kind of systems. Then we looked at the switching properties of this molecule. So Amy converted the bis acrylium derivative into the corresponding bis acridane upon addition of hydroxyl ions. So we can clearly see the dearomatization of the acrylium cores by proton NMR spectroscopy and also by UV visible spectroscopy, since only the transitions centered on the acrylium cores are affected. So we do have dearomatization. Then also this system proved to be fairly robust. So you can add TFA, you restore the acrylium cores with no real demethylation of the porphyrins. So that was a good surprise to us. Then this new receptor, bisacridane receptor, can interact with the same ditopic ligand. And in this case, we were able to estimate a binding constant of 1.3 10 to the 5 molar minus 1, which is about 20% decrease in comparison to the bis acrylium derivative. Then we looked for the electrochemistry. So the bis acrylium derivative has two redox processes, one in reduction, which is the reduction of the acrylium cores, one in oxidation, which is the oxidation of the porphyrins. Then when you add the ditopic ligand, only the oxidation potential is altered because this is one more time where is going to interact the ditopic ligand for the porphyrins at the porphyrins. And also, if you complete the square scheme analysis, you have a new binding constant which is decreased. Then, what was done for the bisacridinium derivative can be done for the bisacridane. So this time you have no reduction potential anymore because the acrylium cores are not there anymore, and the new system has the same redox potential as a new redox potential, which is its own. Then, which is also altered upon addition the same ditopic ligand, and then we end up with a new binding constant. So what we can understand from this is that we can modify or change the binding constant, the affinity between a host and a guest, between addition of hydroxyl ions or by oxidation. So it seems to be quite simple, but I'm going to complexify the picture by summarizing again. So we have a receptor that can interact with a ditopic ligand with a certain binding constant. So then we go for the addition of hydroxyl ions. We change into the bisacridane, and this new receptor can interact with the same ditopic ligand but with another binding constant. Then these four states were brought by electrochemistry, leading to two new binding constants, and instead of having two independent square schemes, they are connected here, leading to a cubic scheme. So if you want, we were able to probe 8 different states for one single molecule. Then we went beyond this. We looked at the field of physics, and for the bisacridane derivative, when you irradiate the bands corresponding to the bands of the porphyrins and you look at the transition absorption, you have a new set of bands increasing, which are the bands of an oxidized porphyrin and also the bands of a reduced acridinium. So this tells you that you have a photo-induced electron transfer that can also be triggered upon addition of the acrylamide cores, which tells you why we have a decrease of the fluorescence of the tweezer in comparison to a model compound. Then we looked also for the bis-acrylene derivative. So these times we have no fluorescence quenching. And even if you irradiate the bands of the acridane moieties, this time you still see the fluorescence of the porphyrins, so which means that you had some energy transfer processes. So let me summarize a little bit again. So we have this receptor that can undergo some photo-induced electron transfer, be converted into the bis-acridane, and do some energy transfer. What was done for the receptor alone can be done also in presence of the ditopic ligand. So this time we have a new charge recombination time for the bis-acrylene derivative and a new quantum yield and a new lifetime for the bis-acrylene derivative. So we were able to probe 4 additional states for this system. I'd like to summarize this story about the acrylamide core. So we started with very simple systems that can self-assemble, nothing too special actually. They can do some self-sorting, which was a little bit more intriguing to us. Then if you go for a fine design of these systems, we can selectively extract perylene out of a complex mixture of polyaromatics, more especially if you use the right solvent, which is perfluorocarbons. Then if you introduce this macrocycle into rotaxane, you have a very complex mechanical response, which can be followed by UV visible spectroscopy and also by electrochemistry. And when you combine a multi-responsive building block with another multi-responsive building block, you have a very complex system showing more than 12 different states. But this story is about to will be repeated again because we have a new little guy in our family and we have plenty of room to expand the complexity of this building block. So I don't know if I have time to speak about the nanocarrays, and maybe I have also a few slides about Strasbourg. Let me know what am I supposed to do.
Sir, you may proceed, sir. No issue, sir.
Pardon me? Can you
Sir,
speak
you may
louder?
proceed. You may proceed.
Okay. So just to mention, because Professor Nagarajan knows these people well, and we were involved in molecules on surfaces using an STM experiment. And the idea came from this man called Christian Joachim to have a nanocarrays of single molecules. So the second edition of the nanocarrays occurred in March 2022. So the idea was to deposit the molecule on a gold surface, a gold 111 surface, and to move the molecule from a point A to a point B. And what you see here are the gold reconstructions. So basically you have a track. So the idea is to use a very particular scanning tuning microscope because you want to see one single molecule, so you have to be under very clean conditions, ultra high vacuum, which is a vacuum of 10 minus 10 millibars. Then also we have some specifications about the molecule, so it should have at least 150 atoms, and that should also be a dissymmetric molecule in order to distinguish the front and the rear of the system. Then we were all locked up for 24 hours. In the same room, and we were controlling our instrument remotely, so from Toulouse, and our instrument was of course in Strasbourg. So 25 teams applied for the call, which was in 2020. Only 13 teams were selected, and finally 8 teams finally were engaged or were involved in the D-Day of the race. So when you were part of the race, what I often say to my students, it's like when you are part of this TV show, you know, it could be a Top Chef or whatsoever. When you are part of the first episode, this means that you've already done something right. So Christian contacted me and he wanted me to be the captain of one of the teams. So I involved Professor Valerie Heitz, who was involved in the porphyrin chemistry. So 2 chemists. We contacted Guillaume Schul, who is a physicist, and he has the STM. and he involved his postdoc, Anna Roslovska. And to understand the behavior of molecules on surfaces, what you need to have is a theorist. So we contacted Xavier Bougie from Toulouse, and he involved as well his postdoc, Hassan Denawi. So the molecule is very simple. What you need to do is to have a very small molecule, the minimum molecular weight to make it move fast on the surface. So that was a bis-iridium complex having an axle in between the two iridium molecules. This molecule has a strong dipole moment because you have the FAC isomers of the iridium complexes. So the three nitrogen atoms are facial. And then on the opposite side, you have three carbon atoms. The design of this molecule is very simple. We have a rigid molecule. It has a strong dipole moment, which is important as well for making it move on the surface. And then why we wanted to do this? First of all, because we were interested in molecular mechanics, so how the molecule behave on the surface. And also my physicist, Guillaume Schul, was interested in emitting molecules on surfaces, and the emission is usually triggered by the tip of the STM. So in March 2022, okay, we had the molecule, we were well prepared, and everything happened in Toulouse, so in this building called La Boule. So if I translate, that means the sphere, because it looks like a sphere, obviously. So that was a former microscope inaugurated by the French president in 1959, so very long time ago. This microscope was functional until 1999. And on the second floor, you have the generator, which looked like this, and if that's fortunate, now it's not active anymore. So the race took place in this area. We had computers to control the motion of the molecule on the surface. So the molecules, they need a fuel to move on the surface, which are electrons, and we had some turbulence. What was very fun during that day that it was broadcasted on YouTube. And the race has started at 11 in the morning. And we were all stuck in this room for 24 hours. So 8 different teams having about 3 to 4 members each. So those were the results we got. So the little thing that you see moving here is actually our nanocar. So we have only one single molecule on this surface, and that's a very large area. So we wanted to be very careful because the idea was to say that if you crashed your molecule, you had to start your nanometrage, if I can say again. So we drove very carefully at an average speed of about 24 nanometers per hour. And at 5 in the morning, something happened. The molecule was stuck on the surface. So this tells you why we want to do this, because we don't understand why the molecule was stuck on the surface. So we still need to better rationalize the mechanical motion of molecules on surfaces. So you can imagine that was 5 in the morning. We drove so slowly that that was no purpose to look for another car. And we went to bed, and to our great surprise, when we woke up, we were reaching a good distance of almost half a micron, and we were on the podium, so the bronze medal. So Anna got the trophy, of course. She was the pilot. We got books. That was broadcasted, as I told you. That was a lot of fun. Just to mention about where I'm from, I guess that's good to share a little bit of my culture. So that's a map of France. If you cut the country in two parts, you have north side and south side. Paris is about in the middle of the north side. Everything which is called, which is west part of France is called the west part of France, and everything which is east part of France is the eastern part of France. Then you have the southwestern part, southeastern part. What about Strasbourg? It's right there, and Toulouse, it's located in the southwestern part. So Strasbourg is the main city of the Alsace region, which is kind of like a small area along the German border, and also Switzerland and Luxembourg. So this area is very famous for its protecting program of these gigantic birds, the storks. This is also where the Bugattis, these famous sport cars, are built in Molsheim, so it's very nearby Strasbourg. It's also famous for its food, which is kind of like a German style food, but in a French way, so a little bit better according to me. And so it's also a wine area, more especially for whites. And usually this region is known for its people who are extremely welcoming. Then what about Strasbourg itself? So it was built on this island that we call, of course, we are very general people, we call it the island. So since Strasbourg was the buffer zone between France and Germany, we needed some fortifications to protect the city. So you have one example. We still have an historical district called La Petite France. And Strasbourg is very, very famous for its cathedral, which was the highest building in the world until the 19th century. Then when the Germans took the city in 1870, they built a new area that they called the Neustadt. So if I translate, this means the new city. And the population of Strasbourg doubled in 30 years. So it has its own architecture, which is classified now. And the city continued to spread in this direction with the European institutions and so on. Strasbourg is also super famous in Europe and in the Western world for the Christmas market. So feel free to come for the Advent period. It lasts for 4 weeks, but I just would like to warn you, it's very crowded. And as Strasburger, we don't like much the Christmas market because we cannot go for doing some shopping in the city center anymore. Then what about chemistry? So when the Germans took the city at the end of the 19th century, they developed also the university with an historical campus. So as you can imagine, we do not run any more experiments there because the buildings are not functional anymore for modern chemistry. So I'm located nearby on the Esplanade campus. And just for the record, there are 2 other campuses, one in north side called Kronenberg. So for those who are interested in C60 chemistry, this is where works Jean-François Niergarten. And then the south part of the city, Nilkirch, we have a campus more dedicated to pharmacological studies. So that's the view of the Esplanade campus. We can recognize the cathedral, the historical campus is right there. I work in this building, which is called the Lebel Institute, which faces what we call the Tower of Chemistry. This is where Jean-Pierre Sauvage, for instance, got his PhD before he was Nobel laureate. And also now, if you wonder where is located ISIS, so the terrorists, they are located right there in this building, so very easy to find them. And this is where are located the most dangerous of them, Jean-Marie Laine, Jean-Pierre Sauvage, and Marty Karplus. So Strasbourg is also a city strongly connected to chemistry, not only because of the current Nobel laureates that we have here, but also because it has hosted some very famous professors such as Louis Pasteur, Charles Wurst, Friedel, Gerhard Fischer, Staudinger, and many others. So I have no time to go through the entire list. So this is the end of my talk. I hope you enjoyed it. Of course, I would like to thank everyone who worked on the project, more especially the students, Johnny, Sonia for the nanocar race, and Amy. I'd like to thank also Valerie for the fruitful discussions I have with her, and the sponsors. And I thank you for your attention, and I will be very pleased to answer to any of your questions.
Okay, everyone. As the speaker mentioned, the floor is open for discussion. And sir, we have one question. In that nanocar race, you have used the iridium complex, right?
Yeah.
Any specific reason for that one? Why it is so specific nanocar?
Because first of all, okay, why do we use iridium complexes? Because first of all, what you want to have is a neutral molecule. I didn't mention this, but when you want to put the molecule on a surface inside the STM chamber, you are not going to open the STM chamber and then do the vacuum again. So you do it under vacuum, under ultra high vacuum. which is 10 to the minus 10 millibars. So to give you an idea, it's about 1,000 times more molecules in the gas phase than it is in the interstellar space. So those are very clean conditions. And so if you want to go for the deposition, now you have only few techniques which are available. What you can think of is sublimation techniques. So if you have a charged molecule, actually you understand that subliming the molecule will be more difficult than it is neutral. So that was the reason why we wanted to do this. Also, the iridium complex, in addition to be neutral, you can control the position of the phenylpyridine ligands. So if it's in a trans environment, you can have a strong dipole moment. And if it's in a mere environment, of course, the dipole moment will be cancelled. So yeah, I hope I was able to answer the question.
Fine, sir. Actually, one more question. Actually, it is related to your slide number 7.
7?
Yeah.
Okay.
In
Should I
that,
share my screen again? Yeah, maybe.
yeah.
Okay, share screen, whole screen. Okay, do you see it?
It's coming.
Okay.
Okay, question is simple. Is there any possibility of polymer formation or polymer product formation? If it is,
I'm not sure I understand. I mean, maybe in this case, right? For the second
yes,
step,
sir.
am I right?
Yes, sir.
So actually, what we do is that we use a huge excess of the dibromo derivative, which is pretty cheap. So we never observed the polymers. So often, what we do see is that we have an extra phenyl ring. That's a very good question, because usually also what you can do is to form the ring, the macrocycle, basically 2 of those. But in our case, we cheat on the conditions, so we use 5 equivalents.
Okay. Okay, one more question. I think it's very lengthy.
So, okay, it's written. Thank you, sir. Excellent presentation. Yeah. Can supramolecular compounds be used for the design and synthesis of COF materials? Yes, there are some examples in the literature, many of them. And so if I may suggest, look at the Stoddard group. They've done metal organic frameworks, many of them having rotaxanes. So I don't see why COFs wouldn't be able to be made. Then are there specific types of supramolecular systems that are more suitable for COF formation? And how do solvent choice of reaction conditions influence their crystallinity? Have you an idea, sir? So, okay, the best for COF formation would be most likely a 2-rotaxane, because rotaxanes, they might be linear and very rigid. That was also the work of, let me think, the work of, so someone did it. And also a friend of mine did it in Marseille, David Bardelon. So yeah, we can think of rotaxanes. This might be better. And then in terms of solvents, so what you have to understand is that you start from an assembly, okay, it's dynamic. But then for the rotaxane or CUTN, which are 2 rings, it's just a molecule again. So you can put it in any other solvents, any solvents you want. You won't be afraid to dissociate anything. So I guess you can use the solvent you want, almost the solvent you want. Of course, you might affect slightly the interaction within the assembly, but I don't think it's going to be a big deal, at least for the COF formation.
HP, excellent presentation. Thank you so much.
I'm so glad to see you.
Yeah, after a long gap, just I'm listening to you. It's nice, excellent work, and the way in which in-depth study, right? It's great. And what about the molecules? You have made macromolecules, right? Many of them. So what about the relative yield and yeah, purification and all?
Yeah, so I mean, in our field of research, I mean, you know it well. The yields are not so important. What matters is to have enough material to run the characterizations.
Yeah.
So, for instance, if you look at the porphyrin synthesis here, we have a yield of 12% for the formation of the porphyrin. For sure, it's the limiting step, but still, we can still work with this and run many different applications. We are more how can I say? We are more thinking of the physical chemical properties than having a molecule in a very good yield. We are not in the field of catalysis, where you should have 80 or 90% yield. Then in terms of purification, I would have to say that most of charged molecules are very easy to purify.
Yeah.
No big deal. You can play with the contour ion, with solvents, very easy. I mean, the problem was once again with these porphyrins, because I didn't mention, but we played with the length of the chain, and if it's too short, the molecule is not soluble. If it's too long, the molecule is not soluble again.
Yeah.
So you need to have to find the right balance. Yeah, it's a problem of solubility.
Actually, one more thing. You worked on the CV studies at a different temperature for one molecule. I don't remember. What about the temperature variation and? Yeah,
So
you said
very
low
good
temperature,
question.
high temperature.
So the temperature variation was from plus 30 to minus 30. So why
30.
were you? Yeah, why this? Because we were limited by the solvent.
Right.
Only this. Then also what you have to take care is the counter electrode. So no, the reference electrode, which was silver. So the potential of silver, I mean, how can I say, type 1 electrode drifts with temperature, so it's not a good idea. So that's why we introduced ferrocene to calibrate, the curve at each temperature. And then also the problem was, the question we had is, what happens for the shift here? Could it come from a drift of the redox potential of just the acrylium unit itself, alone? So what we've done is that we looked at the model compound, so just this 9-phenyl acridinium core, and actually we have just a very small shift of 3 millivolts. So the shift we see for the dimer comes from the dimer formation. This we are sure of this.
Right.
Yeah, and of course that was a lot of control experiments. Yeah.
Good. So any other questions from the audience? Others?
So I guess I saw one, slide 47. If you allow me to answer, yeah.
Yes,
Yeah, please.
So 47. So okay, thank you. One more question. Slide number 47. Can the radical ion quantum yield be calculated for crystal or solid form? Good question. I guess I never thought of this. I mean, Nagarajan, maybe you have the answer. So what I know is that we can photoconvert crystals. This has been done with diarylethin, no problem. But the quantum yield itself, I mean, I'm not convinced. But maybe that could be done actually, because what we do for the quantum yield of photoconversion is we looked at the solution, we put two samples, a reference compound and our compound. We irradiate for the same amount of time with the same lamp at the same distance. And then since we know the quantum yield of the reference compound, we can reach the quantum yield of our derivative. But in the crystal structure, I guess, I mean, I wouldn't see why it wouldn't work. If I may suggest, there is the handbook of photochemical conversions or something like this. and that's very good book. It's very nicely written. So if the answer is not inside this book, I mean, I cannot know.
Yeah. Any other questions?
No, sir.
Okay. So in the absence of further questions, so let us thank Professor HP for sparing his valuable time with us. Hopefully, whether you had lunch or not.
Oh yeah, already. Yeah, it's
You had lunch,
4:20
it's
here.
evening.
Yeah, it's 4:20 p.m. So yeah,
4:20.
fortunately I had lunch.
Right. So thank you so much. Really, I'm very happy to know the kind of work you are pursuing. Really tough molecules and the kind of chemistry and kind of publications, whatever you have made it. Really, I'm very happy to see that. Congratulations to the entire team. And on behalf of the organizing committee, I thank wholeheartedly for accepting my invitation and sparing your valuable time with us. Thank you so much, HP. Thank you.
Okay, thanks to you guys.
Thank you. So,
Have a great
Adra,
day.
you want to
Have a
say
great day.
something? Formal thank you. Yeah, you can propose thanks.
Thank you, sir, for your valuable speech. Now, I request all the participants to join the meeting by tomorrow 6 p.m.
Okay, thank you so much. Okay, thank you all. Okay, bye HP. Bye.
Bye bye.
Bye. See you.
See you.